Signature malleability. You've most likely heard of this exploit, but maybe you don't understand what it is, or maybe you know how to find it in a smart contract, but you don't know exactly why this exploit exists under the hood. In this video, I'm gonna change that. This is my best attempt at demystifying the notorious signature malleability exploit. But first, who am I? My name is Owen. Over a year ago, I founded Guardian Audits, and since then we've uncovered dozens of critical vulnerabilities from auditing hundreds of smart contracts. My goal is to distill down everything that I've learned from over 1,000 hours spent auditing smart contracts and deliver it to you so that you can ultimately become a much better smart contract auditor than I ever could be. All right, let's not waste any more time and let's dive right into signature malleability. Okay, so as you can see, we're in our trusty whiteboard today. We're gonna start off by going over an example of signature malleability in a smart contract in the wild, and then we're gonna dive in and explore some basic elliptic curve cryptography to understand exactly how a signature can be malleable. Fantastic, so here is a vulnerable piece of code. Can you spot the attack? Yes, the signature is malleable, of course. The owner provides the V, R, and S components of the signature, but the attacker can then observe these V, R, and S values, craft another signature that also recovers to the same owner address, and essentially execute the owner's message for a second time, double spending from this contract. But why is this actually possible? How can an attacker observe these values and then create a second valid signature? To understand that, we have to break down how message signing works in Ethereum. And to understand that, we need to start off by looking at an elliptic curve. First, for some context on elliptic curves, go ahead and watch my elliptic curves basics video. I'm going to assume that you know all of the basics of elliptic cryptography from a very high level without any of the in-depth mathematics, of course, as I continue to go through this video. Okay, great. So if you'll indulge me, here is a rough sketch of the SECP 256K1 group, which defines a group of points which happen to lie on a elliptic curve that is governed by this equation here. Now, just some high-level important characteristics of this group and this elliptic curve is, of course, the P, which is a very, very large prime number that we are applying the modulo to. And of course, N is the size of this group and essentially the number of points that lie on the elliptic curve. So with that out of the way, let's talk about ECDSA, the elliptic curve digital signature algorithm, and how the V, R, and S values are involved in this. First, when we go to basically sign a transaction in Ethereum, we already have our private key E that only we know, and then a public key, capital E, that we're able to share with anybody, right? And because of the basics of how the private key generates the public key on the elliptic curve, which I cover in the elliptic curve basics video, when we share our public key, we can be sure that the private key is safely only knowledgeable to us. But when we create this V, R, and S signature that we're going to basically transmit in our message, we're going to sign it by using our private key. So there actually has to be some confounding random value that makes it impossible for an attacker to observe our V, R, and S signature and then backtrack it and uncover our private key. So what happens when we make a Ethereum transaction is we actually generate a completely cryptographically safe random private key. And then from that random private key that is temporarily just generated for this particular signing, we use our elliptic curve multiplication to generate a public key that corresponds to the temporary private key. So we'll call this temporary private key little k, and the temporary public key will be capital K. So it's important to remember that our private keys and our public keys are isomorphic. They're basically just mappable to any point on the elliptic curve, right? So in ECDSA, what we'll do with this capital K temporary public key is we actually take it, treat it as the elliptic curve point. So we have an X and a Y value that lies on the SECP 256K1 defined elliptic curve. This is a member of that group. And we're going to take the X value, and this is going to be our R value in the V, R, and S digital signature. Then once we've defined our R, we can use this formula to compute the corresponding S value. And then now that we've got our R, we can use this corresponding formula to compute the S value that's associated with that R value. Without getting too stuck in the weeds on this S formula, this basically just shows that with elliptic curve addition and the right S value, you can actually yield the public key that corresponds to the temporary private key. And then we've taken that relation and basically just solved it for S. So now we have our S and our R values. Now to understand the V value, let us first just take a glance back at the R value. So the R value is the X coordinate of the temporary public key. So let's visualize what this public key actually looks like on an elliptic curve. So we know it's an arbitrary point on the elliptic curve. Let's just define it as right here. And it has an X value. But we notice if we draw a dotted line right here on the same X value, that there's actually 2 points on the elliptic curve that correspond with this X value. And there will always be 2 points since the elliptic curve function has a y squared and it is reflected over the x-axis. So what this means is that just by using our R value, it's ambiguous which of these 2 points we actually used on the elliptic curve. And so this is where our V value comes in. The V value essentially just allows the verification of the ECDSA signature to be a lot quicker. Now when we attempt to recover the signer of this particular signature, we don't have to check both of these public keys. We know exactly which one to use depending on the V value that we get. But actually, the fact that there are 2 valid points on the elliptic curve that have the same R value is exactly what yields our signature malleability. It turns out that an attacker can actually very easily compute the corresponding S value that would work for the opposite temporary public key and provide a second valid signature that also recovers to the same signer. So right now, let's actually just hop into a node shell and we can actually perform this malleability right now. Okay, I'm going to start off by just importing a few cryptographic packages that we're going to need. They're going to help us interact with elliptic curves and perform common elliptic curve addition and multiplication and things like this. Then I'm just going to get some variables that are characteristic to the SECP256K1 group, such as n, which is, as we know, the order of this group. And then now I'm actually going to define an arbitrary private key that we can use to sign a message. Cool, and now I can get a corresponding public key from our private key, and we're going to use this in the ECDSA signature. And I can actually check out exactly what the public key looks like. As we can see, this is a point on the elliptic curve. It has an X and a Y, and these are represented as big numbers. These are very large, too large to actually represent as just plain numbers in Node. So now I'm just going to define an arbitrary message that we're going to use to sign. So I'll do const message equals 1, and then I'm going to add an n just so it can be a big number, and this is going to make it easy for us to just interact with. And now I'm going to actually create the signature of this message. So I'll do ec.key from private, and then we'll do our private key, and we will sign the message. And we can actually look at this particular signature object, and we have an R and we have a corresponding S value. And you can see that these are both very large numbers, but you'll notice that there is no V value. This is because the V value is actually not necessary for the recovery, but it just helps make the recovery more efficient. Now, if we go ahead and try to verify this, we verify our message matches with the signature and the public key, we can see that it recovers to true. And in fact, if I try to go ahead and change the message, let's say I make it 2, it's going to recover and say that it's false, right? Because the signature was not for that message. Now is where the malleability comes in. I'm going to first grab the S value from our signature, and then I'm going to actually sort of tamper with it and find a different R and S that are actually going to be also valid and recover to a valid signature for the same message. Okay, so here is our manipulated signature. You'll notice that all I changed from the old signature is the S value. And specifically what I did is I took N and I subtracted S. Now we'll remember that N is the order of the SECP256K1 group, or the number of points on the elliptic curve. Now, without getting too far into the group theory, into the number theory, into the elliptic curve cryptography, I'll suffice to say that the modular nature of SECP256K1 allows us to have an S value that is greater than N divided by 2, which is valid for one of the R values, and then an S value that corresponds, which is less than N divided by 2, which is valid for the other R value. So if I do N minus S, I'll actually get that other S value that's on the other side of that N divided by 2. And since we're modding by N, no matter which side my original S was on, I'll always get the other S. So I'll go ahead and define this signature here. And if I go ahead and attempt to now verify that this second signature is also valid for the message, we'll see that it recovers to true. So this is a second valid signature that can be created for the same message. In this contract's case, from the beginning, we can see that this second combination of V, R, and S allows an attacker to observe a previous V, R, and S signature from the owner and trigger another expenditure and essentially double spend from this contract and provide their own tampered V, R, and S version, which will recover to the same owner address, and then they can essentially double spend from the contract. So what is the solution here? The most widely accepted solution has been to restrict the S value to 1/2 of the range, right? So instead of there being a valid S value that's in the greater side of N divided by 2 and a second valid S value that's in the lesser than side of N divided by 2, now when you bound the range, you say we're only going to accept S values that are greater than or less than N divided by 2. You can see here in the Open Zeppelin ECDSA library that this S value is required to be on the greater side of N divided by 2. So in this case, when an attacker attempts to provide a manipulated signature that uses that S value from the lower side of the N divided by 2 range, the transaction will simply revert. And there it is. That is everything that you need to know about signature malleability. If you want to learn more about all things Web3 security related, go to lab.guardianaudits.com and apply to join our community of like-minded, aspiring and practicing auditors, where you can team up to form practice audit teams and do audits of real protocols with other aspiring growing auditors. And you can also get the opportunity to participate in what we call shadow audits and basically come on with our team and do an audit of a real protocol and work alongside professional auditors. And you'll also have access to hundreds of experienced smart contract auditors and Web3 developers where you can ask any and all questions that you have, Solidity and security related. All right, that's all I have for this time. I'll see you in the next one.